Validation of metal alloyed powder core under pulse condition, J.C. Sung from Bs&T in Frankfurt. As engineer and physicist, I started my career with Philips' ferrite division, manufacturing ferrite in Hamburg and designing ferrite in Eindhoven. 3F material at that time already developed for megahertz application, resonance converter. I took charge in sales of European sales of Red Glass, which is a division of Honeywell, and worked also for Hitachi Metals. They give me the chance to get in touch in fine nanocrystalline materials. In the following step, I worked as a marketing manager in vacuum schmelz for Vitroperm 500F components. 2015, I established a company called Bs&T in Frankfurt, which is specialized in field of testing, validation and testing of magnetic materials for high-frequency applications. Here we have outlines for the next 30 minutes. We're going to talk standard, typical value, limit value, the challenge of the validation technique, and afterwards I'm going to make a proposal with a bipolar pulse technique. We take example as metal alloyed powder coil to demonstrate the data processing, and closed with a take-home message. In this slide, we see two columns. On the left side, there's labeled with green color. It is about characterization of ferrite materials and ferrite cores and the sinusoidal magnetization mode. This is further divided into two subdomains. One is related to the low excitation, governed by the IEC 62044/2, mainly performed by bridge, small signal, some single digital of volt or ampere. The high excitation is governed by the IEC 62044/3. The power loss is performed driven by the B mode and the sinusoidal voltage time diagram. At the same time to the power loss, the amplitude permeability is measured as well. The flux density measurement is performed or driven by the H mode. That means the current time diagram and the sinusoidal condition is performed. 2016, we introduced a BST Pro. The loss measurement, the loss parameters extended with another dimension, which is BC bias. The mainly difference between the ferrite characterization and alloy characterization is a result in the temperature dependence. In this context, it is helpful to mention, beside of the Technical Committee 51 dealing with ferrite characterization, the Technical Committee 68 deals with magnetic alloys, mainly silicon steel and different other alloys. So in the Technical Committee 51, there's further 3 working groups divided. One is working group 1 is dealt with magnetic materials. Working group 9 is magnetic components. So the magnetic components is mainly designed and validate under pulse condition. Therefore, we introduce on the right side, on the right column of these slides, the pulse tester. The pulse magnetization shows faster transit of magnetic status. The dB/dt rate is illustrated by the discharge voltage, and there's also IEC or IEEE standard available to describe the physical principle. The concept of permeability to describe materials is overtaken by inductance concept to describe nonlinearity of magnetic materials, which we're going to show in the next few slides. Soft magnetic cores and soft magnetic components show saturation. The nonlinearity is articulated by the inductance concept. The inductance concept is a parallel concept as the permeability to describe material nonlinearity. The material nonlinearity is normally illustrated by the BH loop and BH curve, particularly for soft ferrite. The temperature influence is huge. Being anti-ferromagnetic materials compared to the ferromagnetics to the alloys, the ferrite has lower Curie temperature and lower flux density, and therefore the loss measurement is all this measurement validation technique is very sensitive towards the thermal dissipation during the measuring interval. I take two slides from standards. This one is to distinguish the typical and limit value. Limit value is foreseen with tolerance. For the material, the limit value is almost related to smoke signal measurement performed with ACR bridge in combination with temperature chamber, and these measuring conditions is very much allocated within the relay area. The relay area for ferrite material is around single digital or double digital of amp per meters. That is a problem for the metalloy powder coil. We're going to mention this in the following slides. For shaped cores, the AL value is specified as the limit value. Interestingly, the loss density is either located in the typical value and located in the limit value for shaped cores. For magnetic components, as working group number 9, there's hardly anything available in the standards. In the community of the winding companies, they are dealing rather frequently with current rather than to inductance. Such definition like rated current, saturation current, arbitrarily defined by each company by themselves. It doesn't help very much to have the transparency on the community. It's a big challenge to validate the low permeable materials accurately. Like metal alloy powder core, even their use over half centuries, the classification is still at the beginning. It is decided by the committee the metal alloy powder core is going to be classified under ferrite standards. And ferrite standards is well established over 30-40 years. The original of ferrite is rooted by the coercivity lower than double-digit amp-per-meters. Therefore, the small signal measurement can be performed by the ACR bridge. That's not the case for metal alloy powder core. And each material has saturation. In order to see the saturation behavior of metal alloy powder core, people need 100, even 1,000, tens of thousands amps to see the saturation point. We're going to take example in afterwards. We'll take an example like mega flux, which is 6.5 silicon steel. The theoretical saturation flux density is communicated like 1.7 Tesla. You need large, much more than that to see that point. And the metal alloy powder core with the same composition, they are different degree for desired permeability level, like 26, 40, 60, and so on. And it's very difficult to sensitize this with one composition. People need to have different field strengths to see the same flux density point, because this is actually related to the definition of cross-section, effective cross-section. What people measuring are dealing with voltage and current. What people talking and characterize is Tesla and Östret. So the second problem is the time delay, the absolute time delay of two sampling channels that causes inaccuracy. For the material to be tested, like the Kumu or Sandust, they have a phase angle close to 90 degrees. So you can imagine the physical differentiation of the tangent close to 90 degrees. That's huge. So therefore, it's very difficult to accurately measure the loss levels. The third point is the performance shifting due to thermal dissipation, because large current amplitude is in process and the measuring period is physical over there to accumulate the energy. And those energy heat up the measuring devices. So what we need is a solution to cover the large operation range of metal alloy powder core. Some 100, even 1,000 kiloamps per meter is required. We need to eliminate the systematic errors between the two channels. And we need to limit the thermal disturbance to the minimum. Here are the proposal. On the left side is currently people measure the metal alloy powder core with a ACR bridge and bias with number of DC sources. Expensive, takes long time, and is not accurate because of the thermal dissipation. One measurement performed over 2 minutes, and the temperature shift away. The Bs&T pulse is delivers convincing large signal measurement. The physical principle of the damp oscillation process. A thyristor is triggered by the control unit, and it generates a full reversible current. A nonlinear divide and the test with a non-storage capacitor formulate an ADC resonance. The resonance is sampled with voltage and current decay. Through the voltage decay, we are going to evaluate a Q factor or insertion losses. And through the DIDT method, the different number of inductance concept can be data processed. The whole project is sponsored partly by the European government, the Horizon 2020. It's also supported by the VDE, the German Standardization Committee. The metal-alloy powder core are made of powdered metal-alloy materials. The powder is mixed with insulation, then pressed in cores at high pressure. The distributed air gap between the powder modified magnetic properties. As alternative could be stress annealed nanocrystalline tape bond core. Here we have the description of the device and the test. The device and the test consists of two stacked E65X flux powder core, wounded with number of turns 139. And we have here a data sheet from magnetics and anode. The only one magnetic relevant parameters is AL value, but we see a lot of inconsistency. The number one is the effective permeability and the nominal value of AL are not congruent as described. The second inconsistency is that if you build up the Faraday equation between the given informations, which is described left bottom, is also not consistent. Not consistent in the sense that the desired low flux density from IEC 62044/2 is not reached. Here is to say the initial permeability need to be measured lower than 10 kilohertz, lower than 0.25 millitesla. In this case is 0.6 millitesla. So therefore I say that the current IEC standard of ferrite is difficult, can be reached to validate the existing specification of powder core. Here in these slides, you see the result of the Bs&T pulse. On the upper part, you see the voltage decay and current decay. At the first current amplitude peak, you are able to determine the AC resistance. If you have the AC resistance, if you have the voltage, and then it gives you a chance to calculate the different termination of inductance, which is described in the past pages. On the second half of the slides, on the left, there's show the differential inductance versus magnetization current. and with 8% of the AL value can be found somewhere in the range. On the right side of the second part, the insertion losses can be determined and the Q factor can be calculated. You have the AC resistance and you have the inductance. With the given geometric parameters, effective length, effective cross-section, and number of turns, you can integral the voltage over time, get the B, and the H to current relation is linear. Then you are able to draw the demagnetization curve. If you zoom it very closely on the 0 point, it gives a chance to read directly the coercivity and remanence. The pulse amplitude permeability against the delta B and delta H is given as well. The further data processing is so we can still further process data to articulate the softness of saturation. You have the same curve on the bottom side. What you can do is that to build up the two kind of differentiation. The red one is illustrated as amplitude permeability. The green line is differential permeability. For the differential permeability, you see there's two local maximum, and this is the point which is approaching to saturation, and the size of the Gauss distribution reflects the anisotropy distribution, and it gives you the chance to articulate the softness of the saturation. So with those parameters, you can rebuild the BH loop. So with from the Rivas, he introduced the equation as above, with the information of initial permeability, the Rayleigh constant, the Neal constant, and the saturation magnetization. You can build up the magnetization curve and including the loop. I didn't show the loop here, but you can do it. Loss mechanism. There is no micromagnetic models available. The magnetization in ferro and ferrimagnetic materials is not uniform. That means the loss density has no meaning. The magnetization changes are discrete in terms of space and time. Consequently, there is no physical difference between the hysteresis losses and the kinetic current losses. And to separate the loss into different portions is just self-exercising. And the rest, which you don't understand, categorized as anomaly losses or relaxation losses. That's is a very cheap way to deal with complex problem. So only one physical origin of remagnetization losses is the damping of domain wall movement by eddy current and spin relaxation. So the measurement is indispensable to make serious specification with limit values. And if you perform the measurement, please don't ignore the existing standards. That's very important. So since there's no micromagnetic models available, in those models is supposed to be include the impurity, the material quality, the crystal structure of materials and shaped cores, and so the loss mechanism is still not understood. That's hard works for scientific institution and academia. Here you have some take-home messages. The inductor with metal alloy powder core can be specified with damped oscillation. The inductances and Q factor can be specified as limit value. So IEEE or IEC 62367 Annex G with damped oscillation processes, and the typical renormalization curve can be rebuilt with fitting parameters. So more important, the core loss density is specified only under sinusoidal excitation, compliant with 62044/3 as limit value. The DC biased AC loss is feasible with Bs&T Pro. The linkage of reading loss map is reversible permeability, and the differential inductance is given for simulations. But mathematically, the differential permeability and reversible permeability are the same. So end of the presentation. I would like to show some pictures in Annex. Measuring results for loss map for simulation. Here you have the picture of a Bs&T Pro system. It consists of temperature chamber, a digital oscilloscope, a linear amplifier, and DC sources. And you have set of capacitor, bank, to have various measuring points, and the current detection is followed by current probe. So the whole system is compliant 62044/3. The loss map can be generated in the dimension of frequency, flux density, temperature, and DC bias, HDC. So it's complete.